Hey guys, welcome back to General Chemistry. We are going to talk about chemical reactions, and then eventually that'll lead us into stoichiometry. We'll talk about the math with chemical reactions. So first, let's just get introduced to what a chemical reaction is. So in chemistry, hopefully you've seen this already, we symbolically represent everything, right? We don't write out any real words or names or numbers. We always use a symbol to do that. So how do we symbolically represent chemical reactions? Well, here we see the same chemical reaction, and it is depicted in two different ways. So first in this chemical reaction, I see hydrogen reacts with oxygen to produce water. So let's talk about what these symbols and letters mean. So hopefully you're comfortable with the letter and then the subscript. So here we've got hydrogen. The subscript means that there's two hydrogens that are bound together. That's one of the things we learned from the last chapter. So we see that right here. So these white balls represent hydrogen. Here's one, here's two, and they're attached together in a chemical bond. We see the same thing for oxygen. So O2, that 2 is our subscript, and it means that there's two of them bound together. So our subscripts tell us about the identity of the molecule. If I change this subscript from a 2 to a 3, or if I add a subscript of 2 over here to the oxygen, I've completely changed the identity of that molecule. It's no longer hydrogen or water. It's now hydrogen peroxide or ozone or something like that. So the subscripts tell us about identity. The other thing we see here are we see these big numbers in the front. We call these big numbers coefficients. Coefficients tell us about quantity. So this coefficient 2 in front of our hydrogen tells me that I have 2 of these molecules participating in this chemical bond. So here's one molecule, here's 2. So that's what that coefficient stands for. For the oxygen, again, the number 1 is very typically implied. So you could write a number 1 here as the coefficient. That would be fine. But with that implied 1 coefficient, I see that I have 1 molecule of oxygen. And then over here are my water molecules again. Coefficient of 2, I have 2 molecules. Just a little bit of terminology. So we have this reaction arrow kind of in the middle here. Our reaction arrow is really the same thing as an equal sign for a mathematical problem. So that arrow, sorry guys, that arrow separates the two sides of our chemical equation. On the left-hand side, and always on the left-hand side of the arrow, will be our reactants. What are we mixing together? What is decomposing? So the reactant side is going to be kind of the initial. What do we start with? And then always on the right-hand side of the arrow is our products. What are we producing? It could be one thing is being produced. We could produce 2 things, 10 things, 20 things. There's really no rules that dictate how many reactants and how many products that we have. The only rule is that products will always be on the right, reactants will always be on the left. And then the reaction arrow, you could read that as an equal sign, or you could read it as to produce. So that way you know you're going towards the products. Okay. The other thing that you'll see very often, another symbol in chemical equations, is you'll see these letters kind of written after each molecule. Those letters tell us what state they're in. So all of these happen to be in the same state. All of them have a G written to the side. And so that tells me that these are all in the gas state. If there was an L, that would be liquid. S would be solid. And then this last one, we'll see this very often. If there's an AQ written after any of these, that tells us that it's aqueous. And aqueous is just a fancy word for it's dissolved in water. So aqueous solution would be something, or an aqueous compound would be something that's dissolved in water. So just kind of summarizing the fundamental aspects of chemical equations. The reactants are always going to be on the left-hand side. They're going to be the ones that we're reacting together or breaking down. Products will always be on the right-hand side. That's the substance that we are making. The plus, I didn't talk about this one. The plus will separate individual reactants and products. And then the reaction arrow is what separates the reactant and product. That's our equal sign. The relative amounts of each of the reactants and products are represented by coefficients, those big numbers in the middle or in the front. Okay. So now let's talk a little bit more about chemical reactions. Okay. In this chemical reaction, what I have, let me go back. What I have is I've got CH4 is reacting with oxygen to produce carbon dioxide in water. When we write balanced chemical equations, we want to make sure that the number of atoms that we start with on the reactant side is the same as the number of atoms we end with on the product side. Okay, so that is one of the laws that kind of dictates chemical reactions. We can't just randomly make up an atom. It just appears in the chemical equation. We can't make atoms disappear, like poof, they're gone. So let's take a look at this equation. So what you see here is on the reactant side, we've got two oxygen atoms to start with, right? So none in the first none in the first reactant. In the second reactant, we've got two oxygen atoms. If I go to the other side of the chemical equation, the way that's written now, I see that I've got two oxygen atoms in carbon dioxide, and I have one oxygen atom in water. So as this equation appears on the screen, it looks like we started with two oxygen atoms, and then poof, we just created another oxygen atom as the products. And that is not the case. That cannot happen. So what that tells me is this is an unbalanced chemical equation. This is not how the reaction actually takes place. There must be more involved. We could do the same analysis for the hydrogen atoms. So if we look at the hydrogen atoms on the reactant side, there's 4. And if we look at the hydrogen atoms on the product side, there's 2. So again, it looks like we started with 4 hydrogen atoms, and then poof, we just disappear 2 of them, and we're left with 2 at the end. And again, that's not the case. We have to have the same number on each side. Remember, chemical reactions are just simply the rearranging of atoms. So what we start with is what we end with. We're just simply rearranging the way they're all connected. So here is, actually go back. So what we need to do with this chemical equation is we're going to need to balance it. To balance it, what we're going to start with is writing the chemical equation onto the board. So here's our unbalanced chemical equation. The setup that I'm about to show you is tedious, yes, but it's the best way that I know how to balance chemical equations. There really is no shortcut or more efficient way. This is the best way to do it. So what we're going to do is we're going to take inventory on each side. So on the reactant side, I've got carbons, I've got hydrogens, and I've got oxygens. Then I go to the product side, and I'm going to write the same 3 atoms. And pro tip here, I would just write them in the same order. That way you can keep track of them a little bit easier. So the first thing I'm going to do is just take inventory. How many of each atom do I have on each side? So if I look first on the reactant side, I've got 1 carbon atom. I can go to the hydrogens. That subscript tells me I have 4 hydrogens. And then I look at the oxygens, and I have 2 oxygens. Okay. I'm going to do the same thing on the product side. So I come over here. I've got 1 carbon. In my water, I've got 2 hydrogens. And then for the oxygen, just be careful. We find oxygen in 2 different compounds, and this is the best way to handle that. I've got 2 from carbon dioxide. I've got 1 from water, so that's a total of 3 oxygens. All right, now I can compare, and I look at the 2 sides here, and I've got 1 carbon, 1 carbon. Those are balanced. Those are good. Okay. I look at my hydrogens. I have 4 hydrogens on the reactant side. I have 2 hydrogens on the product side. So I know that can't be the case. I know if I start with 4, I have to end with 4. So what I'm going to do is I'm going to say, you know what? I bet it's not that 1 molecule of water is produced. I'm predicting that there's probably 2 molecules of water that are produced during this chemical reaction. Okay. By putting that coefficient of 2 there, that's going to change the number of hydrogens that are produced. So we take coefficient times subscript, so 2 times 2, and now we've got 4 hydrogen atoms that are produced, 4 on the product side. So now our hydrogens are balanced. But by putting that coefficient of 2 there, what does that also affect? Yeah, it also affects our oxygens, right? So we still have 2 oxygens from our carbon dioxide, but now we have 2 oxygens from that water. So instead of having 3, we now have a total of 4 oxygens that are produced. Okay. So go back. My carbons are still balanced. My hydrogens are now balanced. Now I need to take care of these oxygens. So I have 4 oxygens that are produced. I can't start with 2, right? So again, I'm going to make another prediction. I bet that when this chemical reaction takes place, that we're going to have to use 2 molecules of oxygen, right? By putting a coefficient of 2 there, it tells me that 2 molecules of oxygen are going to participate in this chemical reaction. And again, we're going to take coefficient times subscript. So we've got a 4 here. Now we have a balanced chemical equation. We've got 1 and 1 for our carbons, 4 and 4 for our hydrogens, and 4 and 4 for our oxygens. That's a balanced chemical equation. And this box right here was just that check. So taking the number of reactants, the number of products, and just making sure it's balanced. So I drew it kind of as a tally on both sides. Here's a table format that could work really well as also. So whichever way works better for you. So here's just a different representation of the process that we just did. So here was our unbalanced chemical equation where we had, remember, 2 oxygens to start and 1, 2, 3 to end. So this is our unbalanced equation. And we predicted that when this equation takes place, that we're actually going to need 2 oxygen atoms, and we're going to produce 2 water molecules on the other side. So just a pictorial representation of that balancing that we just did. So just a few helpful hints before I leave you to go practice these on your own. Number 1, we're going to write a skeletal equation. So far, I've given you the equations, so that's kind of a silly step. But eventually, you'll have a problem where these equations are written in words, and you'll have to get the equation onto the paper. Step 2, the number for the atoms for the given element is calculated by multiplying the coefficient by the subscript. So when you do start adding coefficients, we're multiplying those 2 numbers. We're not adding them together. If an element occurs as a free element, balance that last. So we kind of organically did this in the previous example, but oxygen O2 was kind of a free atom. When I put a coefficient on that, it didn't change anything else. So those are good options to leave for the end because they're the easiest to manipulate at the end. Okay, and then remember, you can only change coefficients. You can never touch the subscripts. So once you get that skeletal equation onto the paper, the subscripts are off limits. You may not touch those anymore. That's it for this video. I hope you guys found that helpful.